Thank you for joining us on Synthesis Workshop. I'm Matt Horwitz, and in today's installment of our Advanced Organic Chemistry course, I will be your speaker. Today we will be talking about asymmetric epoxidation. Let's take a quick look at where we are in this course as a whole. Today's talk will be a continuation of our asymmetric catalysis module, and we'll be exploring more ways that chiral catalysts can be used to make enantiomer-enriched products. To introduce the topic of asymmetric epoxidation a bit more, it's useful to have a generic reaction scheme to show the primary focus of today's talk, which specifically is the catalytic asymmetric epoxidation of alkenes. Asymmetric epoxidation is quite important as a chemical transformation, as it can simultaneously generate two adjacent stereocenters, both of which bear useful carbon-oxygen bonds. Those stereocenters, once established, can be leveraged to reach a number of different motifs by virtue of the fact that carbon-oxygen bonds can be used to access carbon-nitrogen, carbon-carbon, and carbon-halogen bonds in addition to others. In today's talk, we'll start by covering foundational work in the field, and we'll look at the Sharpless, Jacobson-Katsuki, Shi, and Julia-Colonna epoxidations. We'll then spend some time looking at the contributions of the Shibasaki group to this field, before transitioning to look at the work of Jorgensen, List, and Feng. We'll also spend some time looking at iron-based approaches to asymmetric epoxidation, as well as asymmetric Johnson-Cory-Tchaikovsky or Darzens type approaches at the end. So to kick this off, let's start by taking a look at the Sharpless epoxidation. This is a reaction that was first reported in 1980, and which rose to such prominence that in 2001, Professor K. Barry Sharpless was awarded his first Nobel Prize, which was shared with Knowles and Naori. This reaction converts allylic alcohols to the corresponding epoxides in a highly enantioselective fashion, using titanium tetraisopropoxide, diethyl tartrate as a chiral ligand, and tert-butyl hydroperoxide or TBHP as the oxygen source. One of the things that makes this such an impactful methodology is that everything above and below the arrow is commercial, and this is something that is not so common even today in the field of asymmetric catalysis. There's a useful memory mnemonic for this reaction shown here. When the allylic alcohol is drawn as shown, with the alcohol substituent in the southeast, using plus diethyl tartrate results in epoxidation from the top face, whereas using minus diethyl tartrate results in epoxidation from the bottom face. But why is this the case? In the stereochemical model shown on the right, we can see a dimeric titanium species where each titanium is bound to a tartrate ligand. And by simultaneous coordination of tert-butyl hydroperoxide and the allylic alcohol, it's possible for one face of the alkene to be preferentially displayed to the peroxide for epoxidation. To have a look at a simplified catalytic cycle involving monomeric titanium, the cycle can start by displacing two isopropoxide ligands and replacing them with one bidentate tartrate ligand. Then, it's possible that TBHP may coordinate first and the substrate second, or also the reverse is feasible. In either case, we arrive at a species with TBHP, substrate, and diethyl tartrate attached, which can undergo asymmetric epoxidation. This step results in a species bearing the epoxide product as well as a tert-butoxide ligand, and through subsequent ligand exchange steps, the species can re-enter the catalytic cycle and continue to perform epoxidations. Let's now take a glance at some examples of this epoxidation in action. Unsubstituted allylic alcohol can be epoxidized in 90% EE, and in this case diisopropyl tartrate was used as the ligand. High enantioselectivities were also obtained with a phenyl substituent, or when trisubstituted substrates were used as well. As you can see, it's common for this reaction to be performed at 0 degrees or lower. This method is also frequently used in complex molecule synthesis. For example, in their 2019 total synthesis of nivatetracyclate A, the Kürti group used a Sharpless epoxidation on the tetracyclic substrate shown in order to reach the epoxide product in good yield and enantioselectivity. They were subsequently able to employ a Meinwald rearrangement with ethereal BF3, where the strong boron allulose acid was used to trigger a 1,2 hydride shift that resulted in the formation of the aldehyde and tertiary alcohol moieties in the product. That product was then carried on to form the core of the target. Coming back to our earlier discussion of why asymmetric epoxidation is important, in this case study we can see that both of the stereocenters that appear in the final product were defined through an asymmetric epoxidation, even though the final target doesn't have an epoxide in it. Broadly speaking, whenever a new asymmetric reaction is developed, it's often important to consider what would happen if a racemic substrate would be used rather than an achiral one. In the case of the Sharpless asymmetric epoxidation, it's possible to perform a kinetic resolution when racemic substrates are used. That is to say, when a racemic allylic alcohol bearing a stereocenter at the alcohol is used in the reaction, it's possible to run the reaction to partial conversion and obtain both the enantiomer-enriched product, which results from the fast-reacting enantiomer of the substrate, and also to recover enantiomer-enriched starting material, which results from the slow-reacting enantiomer of the substrate. As a general consideration, we should also note that it's the difference in transition state energies, or delta-delta-G double dagger, which determines the degree of selectivity in these cases. We're talking about a kinetic selectivity, after all. The chiral catalyst can react much more easily with one enantiomer of substrate than the other, and the barrier to reaction is much lower and the reaction is much faster for one enantiomer than the other. And the macroscopic consequence of this is that both the starting material and the product can be enantioenriched when the reaction is at partial conversion. To reduce this discussion of kinetic resolutions with a Sharpless epoxidation to practice, let's take a look at an example. In 2016, Ogura and Kuwahara were able to execute a kinetic resolution of racemic compound A using the Sharpless epoxidation. This allowed them to obtain the enantioenriched epoxide product bearing 3 contiguous stereocenters and around 68% yield, a figure which is based on the amount of the fast-reacting enantiomer which was present in the starting racemate. Then, red Al was used to enable a regioselective reductive ring opening of the epoxide. An iodoetherification could then be used to obtain the tetrahedrofuran core in diastereopure form, with a 42% overall yield for the 3-step sequence, based on the amount of Ra, which was the fast-reacting enantiomer, used in the racemate at the beginning. That tetrahedrofuran intermediate was then used to form the left-hand side of the polyketide natural product ampherionin 4. Changing gears a little bit, let's turn our attention to the Jacobson-Katsuki epoxidation. This is an asymmetric epoxidation that relies on a manganese-salin complex derived from chiral 1,2-diaminocyclohexane. While Jacobson and Katsuki investigated diverse types of manganese-diamine-based epoxidation systems, it's probably fair to say that, to date, it's the cyclohexane-derived system that's gained the most traction in the long run. The trans 1,2-diaminocyclohexane used in the Jacobson catalyst is readily available, and it can be easily condensed with 2 equivalents of an aldehyde to generate the salin ligands. While this asymmetric epoxidation does not require an allylic alcohol, it's still relatively sensitive to the structure of the alkane substrate. In general, the system is working best for Z-alkenes, and conjugated alkenes are normally working better than non-conjugated ones. E-alkenes and terminal alkenes are normally not good substrates for this asymmetric epoxidation. The oxidant used in this reaction can be sodium hypochlorite or bleach, iodosobenzene, or MCPBA. Often, using Lewis-basic additives like pyridine can have a beneficial impact by enabling catalyst turnover. In the case of the Z-alkane shown at the bottom of this slide, the cis epoxide could be formed in 92% EE, which is especially noteworthy when you consider that this is an alkane substrate that doesn't bear any functional groups that can act as covalent points of attachment to the catalyst, like we saw with allylic alcohols in the Sharpless epoxidation. The mechanism of this reaction is generally considered to proceed through a manganese 5-oxo intermediate which epoxidizes the alkane. However, there are 3 major mechanistic pathways this can occur through. First, there's a concerted pathway which involves simultaneous formation of both carbon-oxygen bonds at the same time. Second, there's a potential pathway leading through a 4-membered metalloxetane intermediate, which may lead either directly to epoxide formation or to the generation of a carbon-centered radical. And finally, there's the radical pathway on the right, which is inferred to exist from the fact that some of the trans epoxide often forms in cases where the alkane substrate is part of a conjugated system. In 2009, E.J. Corey published an org-let proposing that the epoxidation transition state, even if it's concerted, is unsymmetrical. One carbon-oxygen bond is going to be longer than the other. The proposal continues that it's feasible that the carbon involved in the longer CO bond will build up partial positive charge in the transition state, which may have a crucial electrostatic interaction with the phenoxyoxygen of the salin ligand. If you follow the mechanistic papers at the bottom, you can have a more detailed look at the mechanistic background of this reaction. The stereochemical models for this reaction often invoke what's called a top-on approach, where the alkane substrate approaches the manganese oxo from above the diaminocyclohexane bridge, or a side-on approach, where it comes in at more of an angle. For example, if we take the SS enantiomer of the catalyst, we can then predict which enantiomer of product will be formed using this model, as long as we orient the alkane properly. And here the key is to make sure that the large alkane substituent is drawn as approaching from the opposite side of the axial methine hydrogen. This logic can be similarly applied for the other enantiomer of the catalyst. We just need to flip the way the alkene is drawn in order for the model to correctly predict the enantiomer of product formed. There have also been some useful stereochemical memory mnemonics for this epoxidation system, which are shown here. For example, if you draw a Z-alkene in this way, using the SS Jacobson catalyst results in epoxidation from the top face, whereas the RR catalyst gives epoxidation from the bottom face. If you go through the exercise of drawing what products you would get from the stereochemical model above, you can see that this matches. As we mentioned before, Trans-disubstituted alkenes are normally not giving high enantiosselectivities in this reaction, although there is still a memory mnemonic available for that case. With that said, trisubstituted alkenes have been shown to work in this asymmetric epoxidation as well, and there's a memory mnemonic here for them. To look at an example of this reaction in action, let's have a look at the Kürti group's synthesis of best phthalates A and B. In this work, they showed that a Suzuki-Miura cross-coupling could be carried out with a decorated aryl boronic ester shown to install a Z-alkene. That intermediate was then used as a substrate for a Jacobson-Katsuki epoxidation, and using the RR catalyst, they were able to obtain the epoxide product shown in 93% EE. The epoxide was then subjected to an aqueous hydrolysis at low temperature in order to obtain a diastereomeric mixture of products, both of which were carried forward by treating with triphosgene and pyridine to form cyclic carbonates. The cyclic carbonates obtained from the sequence were then further elaborated to reach the final targets. To look at a more complex application, let's turn to a case where this asymmetric epoxidation was applied to a racemic substrate as opposed to an achiral one. In 2019, the Bell and George groups applied this reaction in their biomimetic approach to bruciol, which involved using the RR Jacobson catalyst in conjunction with MCPBA and NMO as stoichiometric oxidants to selectively epoxidize the top face of the alkene present in both enantiomers of the proto-bruciol substrate. Each diastereomer of epoxide intermediate can undergo a ring-opening CO bond scission step, which is aided by the adjacent phenolic oxygen. The intermediate formed through this ring cleavage is a reactive species known as an orthoquinone-methide, which in the case of both pathways is well situated to undergo a subsequent hetero-Diels-Alder reaction. In the top pathway, this provided bruciol and 11% yield, while in the bottom pathway, this led to 2'-epibruciol and 3% yield. Here, the low yield was attributed to overoxidation of the electron-rich dioxycoumarin system in the substrate, which made this quite a challenging case. At this point, I want to take a brief detour to look at another major contribution of the Jacobson group to the problem of accessing enantioenriched epoxides. While the approach we've just seen is an asymmetric epoxidation of alkane substrates, the group has also developed a very powerful hydrolytic kinetic resolution, or HKR, of racemic mixtures of epoxides. In this approach, it's possible to convert a racemic mixture of epoxide starting materials into enantioenriched diol products and enantioenriched recovered starting materials, using a cobalt-saline complex. For example, using the SS cobalt-saline complex, we can reach the product mixture shown on the left, whereas with the RR cobalt-saline complex, we can reach the mixture shown on the right. Following the foundational work of the Jacobson group on this reaction, which is exemplified by the 1997 Science and 2002 JACS, they partnered with the Blackman group to look deeper into the mechanism, which is discussed in their joint 2004 JACS paper. While we won't go through that study in detail, it's worth noting that this reaction has been proposed to operate via a cooperative bimetallic mechanism, where one cobalt-saline complex acts as a Lewis acid, and a separate cobalt hydroxide-saline complex performs the epoxide opening in the rate-determining step. While this approach is limited to terminal epoxides, that's still quite a useful category of epoxides when we start to think about how to actually put molecules together. We can imagine that if a racemic epoxide can be generated using a trivial epoxidation system, like MCPBA, this kinetic resolution could then be used to easily enantioenrich the epoxide and reach either enantiomer. Of course, as with any kinetic resolution, the maximum yield is 50% when you start from a racemic mixture, but that hasn't stopped this reaction from being used in complex molecule synthesis. As a case study, in the Mohapatra group's total synthesis of 2E macrolactam-3, the epoxide on top was prepared in enantioenriched form by a HKR using the RR enantiomer of the catalyst, while the epoxide on bottom was enantioenriched from a racemate using the SS enantiomer of the catalyst. Interestingly, the epoxide on bottom was actually used twice in the synthesis, and through a convergent approach, these building blocks were assembled to form the final target, with the carbons highlighted in the product arising from the carbons indicated in the enantioenriched epoxide starting materials. It's also worth mentioning that an asymmetric epoxidation reaction can be applied in sequence with a hydrolytic kinetic resolution. By doing this, it's possible to achieve a yield over 50% for the sequence, even though a kinetic resolution is involved, and this is because the initially generated epoxide is partially enantioenriched in one enantiomer. For example, in the Fürstner group's 2013 formal synthesis of polycavernoside A, the authors used an asymmetric epoxidation of an enide substrate to reach the desired epoxide in around 50% EE. Then, through a subsequent hydrolytic kinetic resolution, they were able to further enantioenrich the desired enantiomer of epoxide while reacting away the undesired one. This sequence was achieved in 73% yield, and provided an important building block that was used to reach a previously reported intermediate for the synthesis of polycarbonatide A, thereby completing the formal synthesis. Changing our focus now, let's turn our attention to the Shi-epoxidation. The Shi-epoxidation relies on a chiral ketone catalyst derived from D-fructose, which in the presence of KHSO5, also known as oxone, or H2O2, is capable of selectively epoxidizing one face of an alkene substrate. Let's take a look at some of the examples of this epoxidation that have been reported in order to get a feeling for the relative breadth of applications this can be used for. Symmetrical dienes as well as unsymmetrical dienes have been shown to be excellent substrates for this reaction, as have trans-disubstituted and tri-substituted alkenes. Cis-disubstituted and terminal alkenes are often problematic categories for this asymmetric epoxidation. To understand a bit more how this reaction is working, let's take a look at the mechanistic cycle. At the top of the slide we can see the Shi catalyst, which can react with oxone to form the adduct shown. In the main cycle, deprotonation of the tertiary alcohol gives an alkoxide which can trigger intramolecular nucleophilic substitution to give a dioxirane intermediate. This dioxirane intermediate is the key to achieving epoxidation on the alkene substrate. We should note that the first intermediate we generated can also undergo an undesired Baeyer-Villiger reaction to form two different 7-membered lactones, and we touched on this possibility in our named reaction episode on that transformation. Coming back to the key epoxidation step, there are two transition states that are worth knowing about, the spiral transition state and the planar transition state. While the identity of the major transition state may depend on the specific structure of the alkene substrate, it's often the case, at least for trans-disubstituted and tri-substituted alkenes, that the spiral transition state is the dominant one. Now let's have a look at another approach to asymmetric epoxidation, which is the Julia-Colona epoxidation. In this nucleophilic epoxidation, alpha, beta unsaturated ketones are treated with hydrogen peroxide, sodium hydroxide, and polyalleucine and toluene in order to reach the corresponding keto epoxide product. As a brief side note, I should also point out that you'll often hear general epoxidations of enones with hydrogen peroxide being called Weizsäcker type epoxidation. The structure of monomeric L-leucine is shown here, and in order to reach the catalyst for this reaction, we can start from the amino acid and treat with benzyl chloroformate to reach the carbamate. Then, the carbamate can be cyclized through the action of thionyl chloride, and the resulting cyclic L-leucine monomer can be polymerized by treating with butylamine as an initiator. To understand a bit more about how asymmetric induction is occurring in this reaction, it's worth looking at the model published by Kelly and Roberts in 2004, in which 3 N-terminal amide NH bonds bind to the hydroperoxide enolate intermediate. On the one hand, 2 NH bonds of the N-terminus bind to the enolate oxygen and form a so-called oxyanion hole. On the other hand, a further NH bond of the catalyst binds to the hydroperoxide moiety and aids in the intramolecular hydroxyl displacement event that forms the epoxide.
After I initially put this talk together, I was talking to a former guest of the podcast, Corin Wagen, who now runs a company called Rowan, focused on enabling computational chemistry through a user-friendly web app. Corin used his site to build this 3D model, which I think shows the interactions we were chatting about just now in a much more clear way. I'll leave the shareable link for this model at the top of the comments, and I'd also encourage you to check out the link for yourselves and play with the model a little bit, and also to see whether or not this site could be interesting for your own research, as it's quite easy to use.
Now, let's see how the Julia-Colona epoxidation has been used in practice. In 1997, it was demonstrated that the tert-butyl ketone shown could be treated with immobilized polyalleucine, or IPLL, urea hydrogen peroxide, and DBU to reach the corresponding enantioenriched epoxide. Then, a Baeyer-Villiger reaction was used to convert the tert-butyl ketone to a tert-butyl ester. Through this sequence, it was possible to reach the product shown in 70% yield and over 96% EE. The product could then be carried forward to reach diltiazem. In this approach, both of the stereocenters that appeared in the final target were set using the asymmetric epoxidation. It was also shown that if you carry out the same reaction sequence on a substrate with an unfunctionalized arene, you can reach the corresponding epoxide, also in good EE, and that building block can then be elaborated to reach the side chain of Taxol. So in the end, even though it may have looked at first like the scope might be quite narrow for this reaction, by employing other functional group transformations, it has also been shown to be quite useful. It's also worth looking at the nucleophilic epoxidation systems of Shibasaki. In 2001, it was shown that lanthanum binyl triphenyl arsine oxide complexes are capable of epoxidizing enones in a highly enantioselective fashion using tert-butyl hydroperoxide. It was demonstrated that both the phenyl groups in the example with chalcone shown at the top could be replaced with alkyl substituents, as we see in the additional examples shown below. Here we can see the proposed active catalytic species, which is thought to activate the carbonyl of the substrate by acting as a Lewis acid, while a lanthanum-coordinated tert-butyl hydroperoxide engages in a nucleophilic conjugate addition. The peroxy intermediate formed through this conjugate addition can then collapse through the attack of the lanthanum enolate on the proximal oxygen, giving the epoxide product. If we compare this to the Julia-Colonna epoxidation, one nice advantage of this chemistry is that it avoids the synthesis of the polyol-leucine catalyst. The Shibasaki group also extended this nucleophilic epoxidation approach to alpha-beta unsaturated amides in 2002, although in this case they used samarium rather than lanthanum. This reaction provides epoxy amides in very high enantioselectivity, and the aromatic substituent in the top case can be replaced with an aliphatic substituent as well. The scope of this report included successful cases with 1 or 2 substituents on the amide nitrogen. Also in this paper, they demonstrated a 1-pot, 2-step sequence consisting of asymmetric epoxidation followed by benzylic CO bond cleavage using palladium on carbon. Impressively, the conditions of the second catalytic step were compatible with the epoxidation conditions, and here's an example which delivered the secondary alcohol product shown in excellent yield and EE. In the area of nucleophilic epoxidation, we should also talk about the organocatalytic approach of Jorgensen. Here, alpha-beta unsaturated aldehydes were treated with a chiral secondary amine catalyst derived from proline, as well as hydrogen peroxide. This reaction provides epoxy aldehydes in high stereoselectivities and good yields, and is initiated by condensation of the catalyst onto the aldehyde. The chiral that forms can then react with hydrogen peroxide to form a peroxy-enamine intermediate, which can collapse to form an epoxide by the intramolecular attack of the enamine on the proximal oxygen. Finally, hydrolysis of the aminium results in formation of the product and regeneration of the catalyst. Here are some additional examples where we can see that the reaction can give high stereoselectivities even when alkyl substituents are used, but the third tri-substituted case was not as successful. Importantly, since this reaction works by aminium activation of the enal moiety, it's possible to carry out this epoxidation in the presence of other unfunctionalized alkenes, as in the example on the right, which was formed from a geometric mixture of alkene isomers. We should also briefly look at the work of the List group, where organocatalytic conditions were developed for the enantioselective epoxidation of cyclic enones with hydrogen peroxide. By using the cinchona alkaloid-derived primary amine system on the left, it was possible to achieve epoxidation selectively from the top face of the cyclohexenone starting material, whereas with the diphenylethylamine trip system on the right, it was possible to achieve epoxidation from the bottom face. The group has also developed a related system for branched enals, which is reported in the 2010 JACs at the bottom. It's also worth mentioning the contributions of the Feng group to nucleophilic epoxidation. Let's have a quick look at some highlights from that group now. In 2012, the group showed that chiral NN dioxide ligands, when used in combination with scandium triflate, are capable of allowing enantioselective nucleophilic epoxidation on simple enones with H2O2. The chiral ligands used in this reaction have also been employed by the same group in a wide variety of contexts in asymmetric catalysis. In 2017, the group demonstrated that this system is also suitable for the asymmetric epoxidation of electron-deficient enines, and in 2021 they used a very similar system to carry out asymmetric epoxidations on terminal enone substrates. With respect to the methodologies we've seen before, this approach is probably most similar to the work of Shibasaki, where a chiral Lewis acid activates the carbonyl to facilitate the conjugate addition of an oxygen nucleophile. And now I think it makes sense to also go through some of the advances in asymmetric epoxidation that have been made using iron-based systems. Since we're really going for a succinct summary and not an exhaustive story of this specific subfield, we'll start in 2001, when White, Doyle, and Jacobson reported a biomimetic catalytic epoxidation system using the iron tetradentate ligand complex shown, acetic acid, and hydrogen peroxide, which was demonstrated to allow epoxidation and good yields for a range of aliphatic alkanes, with reaction times on the order of minutes. Here are some additional examples of the types of products that were accessed in this report. In this study, the authors showed that the active catalyst self-assembles under the conditions of the reaction and is a mu-oxo-carboxylate bridge diiron complex. The acetic acid was found to be critical for reaching the desired active catalyst structure during the reaction. While these epoxidations were racemic, this became a very important precedent for subsequent asymmetric work. For example, in 2011, the Yamamoto group reported an asymmetric epoxidation of beta-beta disubstituted enones. This is an interesting substrate class because, when you think about it, no matter how we orient the carbonyl moiety, there's the possibility to have steric repulsion when the molecule is drawn in a planar fashion. Therefore, planar conjugated geometries are disfavored for these substrates, meaning they could be more suitable for electrophilic epoxidation than nucleophilic epoxidation. In their 2011 report, the group demonstrated that iron triflate in combination with the chiral phenanthrene ligand shown and peracetic acid allowed the catalytic asymmetric epoxidation of the substrate glass. Additionally, they were able to show that the reaction also works with alkene substrates lacking a carbonyl. However, at this stage, there was a bit of an open question about the nature of the active oxidant. Was it really electrophilic? To settle this question, the authors set up a competition experiment between the two substrates shown. One, a beta-beta disubstituted enone, and the other, a trisubstituted alkene. Under the conditions of the reaction, they found that the substrate lacking a carbonyl reacted noticeably faster, leading them to conclude that the active oxidant is indeed electrophilic in nature. We should also mention the work of Gebink and Costas, who in 2016 reported the asymmetric epoxidation of cyclic aliphatic enones using the chiral iron-based catalyst shown. The reaction gave 90% EE when cyclohexenone was used, and also gave good enantioselectivity for other ring sizes and substitution patterns. 2-ethylhexanoic acid was used as an additive in this case, and was found to aid in the controlled activation of hydrogen peroxide. Here, these groups again questioned the nature of the active oxidant, and carried out a similar competition experiment between cyclohexene and cyclohexenone. The result was that the substrate without the carbonyl reacted faster, and actually here the difference in reactivity was even more striking than in the Yamamoto case. This pointed to an electrophilic active oxidant in this case as well. And lastly, I want to mention one final approach to the asymmetric synthesis of epoxides, which is the asymmetric Johnson-Cory-Czakó reaction. While we won't go into this approach in detail, it's worth knowing that sulfonium ilides and aldehydes can react to form epoxides in a racemic sense. And in order to make this approach asymmetric, a number of different groups have developed chiral sulfonium ilides that can provide enantioenriched epoxide products. Some examples of the chiral sulfides that have been used to reach chiral sulfonium ilides are shown here, with the source of chirality varying greatly across the cases shown. If you're interested in this approach, I would encourage you to dive a little bit into the literature cited below. So in conclusion, many methods of asymmetric epoxidation have been developed using approaches ranging from metal ligand scaffolds to organocatalysts, and even including enzyme-like approaches. In the end, though, no approach is completely general, and the substrate of interest is always critical in selecting the most appropriate asymmetric epoxidation method. In the future, we may see work which focuses on methods using catalysts and ligands built from increasingly simple or readily available chiral building blocks. And if you look at this presentation again, you can probably see that over time, the methods that have already taken this into consideration have had the largest impact. Reusability and recoverability of catalysts and ligands will also be very important in future work as we think about sustainability more and more. And of course, it will be very important to reduce catalyst loadings as much as possible as methods continue to evolve towards providing solutions that are applicable on a large scale. And with that, we'll close this talk on asymmetric epoxidation. Thank you very much for watching, and be sure to tune in for our next talk in this course as we continue our asymmetric catalysis module. See you next time!